Professor Doerte Blume. Please, Doerte, go ahead.
Yeah, thank you very much, Tobias. I'm trying to arrange the light a little bit. It seems like there's a lot of reflection. So thank you for having me. And so what I'm gonna tell you a little bit about today is the Efimov scenario, and in particular, the Efimov scenario in the presence of spin-orbit coupling. And so just to put this a little bit into context, of course, you've heard about the three-body Efimov effect. It was really been beautifully introduced by Pascal Naidong, and then also it showed up quite a bit in the discussions of Alejandro Kievsky's talk, in particular in the context of nuclear systems, with the triton being an example of a system that's influenced by Efimov physics. In addition, this morning, Pascal Naidong extended the Efimov effect that was initially introduced for three identical bosons. He extended this to unequal mass systems as well as fermionic systems. And then there was also discussion about 4-body and 5-body and larger body systems and states that are tagged on to the 3-body Efimov states. So what I want to do today is I want to discuss three equal mass bosons, so sort of going back to the simplest scenario in terms of the mass at least. So it means that we will have the magic factor of 22.7 show up. But I do want to add a single particle term, actually three different single particle terms to the Hamiltonian. And these are so-called spin-orbit coupling terms. And this is not the type of spin-orbit coupling that was mentioned in the context of nuclear systems. This is actually a spin momentum coupling. So it's a coupling between the spin degree of freedom. In fact, it will be a pseudo spin degree of freedom and the motional degree of freedom. So it's really it's not gonna be sort of what you might be thinking of, which is an L dot S coupling term. This is what you would see in nuclear systems, but it is actually a coupling term that goes as P dot S, where P is the momentum, S is the spin. And this is the type of spin-orbit coupling that you would usually find in condensed matter systems. Okay, and I will be discussing this in the context of ultra-cold atom systems. Then the other thing that we will see today is I'm going to discuss one two-body or few-body technique today. It's a little bit different from the hyperspherical harmonic approach that was discussed earlier by Alejandro Kievsky. The stochastic variational approach was alluded to and discussed a little bit yesterday already in one of the contributed talks. Okay, so just to give you a little bit more of an overview of what to expect. So the way I sort of set it up is I want to review just a few key aspects of the three-body Efimov scenario, the simplest case, three identical bosons. And then I want to discuss what is this 1D spin-orbit coupling that we're adding to the system. So essentially what this spin-orbit coupling term does is, just to sort of give you a little bit of a heads up already, what it does is it takes our normal dispersion relationship. So it takes the free particle dispersion for a single particle, which is p squared over 2m, and it actually modifies this to something that's a little bit more complicated. And I'm going to discuss what this is. And so the key sort of thing to keep in mind here right now is that What we are modifying is really the single particle dispersion. And this means that we really have to work a bit to understand the single particle problem. So that, that's nice, because one body physics is typically a lot simpler than two or three body physics. So this shouldn't be too bad, but we will see a dispersion relation that's a bit unusual. And then since the single particle dispersion has changed, this also means that how the two-body bound states and the three-body bound states will change. And then the natural question is, okay, in the three-body sector, will we still have an Efimov effect or not? So this is sort of the idea. And then, just sort of in a way as an aside, since we do want to solve the two and three body problem, we do need to think about the numerical method that can be applied. And so I will introduce one technique a little bit. So there are sort of two things that I want to point out about the topic for today. Sort of in contrast to what I discussed on Monday and Tuesday. First of all, I'm going to be discussing stationary systems today. So there's not going to be any time dependence. So that's different from what I discussed on Monday and Tuesday. And the other difference is that while what I discussed on Monday and Tuesday was very strongly influenced by experimental results, and I really tried very hard to make a connection with experiments. What I'll be discussing today is not directly influenced by experiment. In fact, the three-body Efimov effect in the presence of spin-orbit coupling has not yet been observed experimentally. So this is sort of something that's still outstanding. What I should mention is that this synthetic spin-orbit coupling has been realized in cold atom systems. It's just they haven't looked at the ThreeBoson, the three-body Efimov effect. So this is sort of where we are headed today. So let's see how we're going to start. And I said, well, to start with, what I want to do is I want to review the ThreeBoson system a little bit, just so that the sort of language that I use to describe it, which is actually very similar to how Pascal and Alejandro discussed the three-body Efimov effect, but just to sort of set the stage for what's going to come afterwards. And so to start looking at the system, I just wrote down a generic Hamiltonian here. So this is the normal kinetic energy here. So we have the kinetic energy in the first interparticle distance coordinate here. It's our first Jacobi coordinate. This is our second Jacobi coordinate, and this is the kinetic energy associated with the second Jacobi coordinate. The center of mass has been separated out. And then we have a sum over zero range two-body interactions. And then to sort of stabilize the system, to make it tractable, I've added a three-body force here, and very schematically, I've just written this three-body force or this three-body potential as a product of two delta function interactions. And again, this is also something that was already in Pascal Naidong's talk. So the first question that I want to ask is, okay, what are the units of G2 and G3? I think if you paid attention to the previous talks, or if you just do dimensional analysis, then you should have this. So, okay, we got an answer there. This G2 was suggested as energy times length, and that's almost correct. There's one difference here compared to what we had previously. Let me just highlight this, and I was a little bit sloppy in writing this. this is really the 3D delta function here, because I'm now working in 3 spatial dimensions and not in 1 spatial dimension. And this means that this delta function here has units of length to the -3. And so if we take that into account, this means that the suggested answer has to be changed to energy times length to the power of 3. Does that make sense? Great. And then we can apply the same logic here, right? We have length to the -3, we have length to the -3. So in the case of G3, we need energy times length to the power of 6. And again, this is just sort of the if you want generic Hamiltonian, then we can look at, and that is used to discuss the Efimov effect. And of course, the next thing is to sort of really look at the coupling constants. This G2, you've seen a number of times already. This is most frequently written as 4 pi h bar squared as divided by the mass. And if we do this, we just get a scattering length of as. And now, sort of, I just answered this first question here. What is the most general expression for G2? So if we want to write this in general without using the scattering lengths already, then this would say that we should be thinking about h bar squared times a length divided by the mass. And the factors of 4 pi, we just put in sort of in a way for convenience. So the most general expression here for the G2 would be h bar squared over m times the length. And so by most general here, I just mean to make the units of the problem correct. And so similarly, okay, that's a question. Can we modify momentum by incorporating a coupling similar to a quantum harmonic oscillator? Sure. So I think what the question might be getting at, and correct me if I'm wrong, if I write down my Hamiltonian and I say I have p squared over 2m, and now I add a harmonic oscillator or potential to it, that's 1/2 m omega squared x squared. In this case, the momentum is, like this momentum here is no longer a conserved quantity. There's a coupling between momentum and the position. Is this what you're thinking about, Soros? Yeah. So the sort of key difference in the spin-orbit coupling case is that what we're going to do is, if you think about this harmonic oscillator that I just sketched here, the idea here would be that we have, say, a single particle, and that particle is sort of moving in a trap, right? We're looking for the, say, wave function of this particle in our harmonic oscillator. Now, when we have, just sort of looking ahead a little bit, when we do have the coupling between the momentum and the spin, then, of course, I have to tell you what type of spin we're going to look at. And we're going to look at a spin 1/2 particle. And so what this means is that our particle will now have sort of, say, a spin up and a spin down component. And now the motion for our spin up degree of freedom and our spin down degree of freedom are actually coupled. So in some sense, you can think about this in analogy to the nuclear system, where we have different isospin projection quantum numbers. So we do have different spin channels in our problem. But in the nuclear case, the coupling is not coming in through the momentum, so through the motion of the particle per se, but through an orbital angular momentum. And there are actually significant differences. You might say, oh, what does it matter, right? I can use either momentum and couple this, or I can use an orbital angular momentum and couple this. But there are significant differences between a momentum and an orbital angular momentum. And to see this, the fact that there are actually differences, we, might just think about the problem classically. So let me actually maybe insert just a page here. If we think about this classically, right, what is our momentum? Okay, so momentum is m times v classically, and this is just m times r dot, right? So now, what is orbital angular momentum classically? Anybody? Okay, we have r cross p, right? And this means we have m r cross r dot. Okay, so now let me make a transformation and let me take r to minus r. What happens to our momentum when we make this transformation? Well, change the sign, exactly, great. So when we do this here, we pick up a minus sign. So let me just schematically indicate that here. So what happens to our our orbital angular momentum when we make this transformation? Okay, so that's too simple now. We don't get a sign change, right? So in this case, so let me just indicate this here. So what you see is that under very basic transformations, the momentum and the orbital angular momentum are really transforming differently. And this means that the sort of physics that we see in an L dot S coupled system is actually different from a P dot S coupled system. And that's something that's really important to keep in mind. So the spin-orbit coupling that we have typically in both atomic physics and nuclear physics, actually quite different from the spin-orbit coupling that we usually or that we tend to encounter in condensed matter systems. Okay, so let's get back to this part here, where we were discussing sort of the most general expressions for G2 and G3. So we already answered the most general expression for G2, so that's given here. And of course, if we look at this and sort of generalize this, then if we look at G3, then we find that in terms of dimensions, we need an h bar squared, we need a length to the 4, and then we need to divide by a mass. And that's exactly what we find, and that is what I wrote out here on this slide here. So this is just sort of to say, okay, you know, we have these coupling constant, there's a two-body coupling constant, so what we expect is this two-body sort of length scale that's coming in, so that's the S-wave scattering length. And then we have a three-body coupling constant, and so we expect some sort of length scale from the three-body problem to come in. And of course, it was beautifully discussed earlier in the talks that this is sort of gives rise to the so-called three-body parameter. And indeed, what we tend to use is we tend to use this kappa star, which has units of inverse lengths. And then we write our coupling constant in terms of, or at least frequently, that's what we choose. We write our coupling constant in terms of the energy at unitarity, the energy of one of the three-body states at unitarity, that is when the S-wave scattering length is infinitely large. Okay. So this is just sort of reminding you of our scales. So I'm going to use this kappa star here to denote, to re-express one of the energies of the three-body problems at unitarity. So the other thing that you remember from the three-boson problem, and that was discussed already very nicely, is that there's actually a continuous scaling symmetry in the problem. So if we scale time in this way, position in this way, scattering lengths in this way, energy in this way, and this kappa star in this way, then the solutions to the time-dependent Schrödinger equation remain unchanged. And Alejandro Kievsky really took a lot of it, took advantage of this continuous scaling symmetry when he sort of discussed how to move the dimer along the axis, sort of saying that there are a lot of similarities between, say, the helium dimer and the deuteron. Now, in addition, and this gives, this is associated with the Efimov effect. In addition, one can show that when we have this sort of a situation, that the Schrödinger equation possesses a discrete scaling symmetry. So now this parameter lambda, I call lambda naught, takes a very particular value. That's this 22.7 roughly, and there are many, many digits. This comes out from solving the hyperangular eigen equation for zero-range interactions. And now if you look at this discrete scaling symmetry, the terms that the sort of pieces that I wrote here in blue are exactly the same as we have in the case of the continuous scaling symmetry. However, the kappa star does not actually get scaled. And as you've seen previously in the previous talks, this is associated with the existence of three-body bound states that are discretely related to each other. That is, if we know the energy of sort of one three-body system as a function of scattering lengths, if we are within the universal window, we know the energies of all the other three-body states, namely the higher lying excited states. And of course, you've also seen that if we are at unitarity, there's an infinity of three-body bound states, especially, or in particular, if we don't actually impose an energy cutoff. So we really work within a zero-range framework, and we don't use finite range interactions. Sorry, let me rephrase this because I didn't word this very well. So we always have an infinite number of three-body bound states at unitarity. What I meant to say is that if we have a finite range interaction, then we have an infinite number of states going toward threshold, but we actually have a cutoff in the high energy limit. And I come back to this, or I can actually illustrate that in this plot here. If we do have a finite range potential, then some of the lower lying states like this one here or this one here would be non-universal. So these would not be Efimov states anymore. But still, even for a finite range interaction, we would have an infinite number of states. So an accumulation of an infinity of states as we go toward the unitary point. Okay. But before I discuss this, let me sort of, again, just to remind you what we already understand about the three-boson problem. Let me just remind you again where this factor of 22.7 comes from. That comes from solving the Schrdinger equation in the hyperangular degrees of freedom. And if we do this, then for the 0+ channel, so orbital angular momentum is 0, parity is even, we get this S0 value, which is, it's just a solution to a differential equation, but it certainly plays an important role in the three-body problem. And that value of 13, and this value of 1.006, so on, is then what enters into the hyperradial Schrödinger equation. And that is the equation as we, that sort of most immediately tells us that there's something going on, because we have this 1/r² potential, this hyperradial potential, and this is where we then see this infinity of states showing up. It's sort of like a comb of energy levels that if you shift them by a discrete amount, all the energy levels line up again. And that is this discrete scaling symmetry. Okay, and again, these are things that you'd already heard earlier. I just sort of wanted to discuss it sort of in my own way. And if we look at the results, and again, I'm going to show this because later on I'm going to sort of generalize this to the system with spin-orbit coupling. When we look at the results, this is sort of what we see as a function of scattering lengths. We see the sequence of three-body states. So as I said earlier, there's an infinity of them. On the positive scattering length side, these three-body states merge with the two-body continuum. So here we have that dimer, that's that dashed line. So this is our dimer. Remember, I'm plotting the square root of the energy here. And so this is where we have a continuum here. And then up here in this regime, the trimers are merging into the 3-atom continuum. So here we have 3 atoms that are separated, and in this regime we have the dimer that's separated from the atom. So we also have a continuum, but it's the atom dimer continuum. So the key thing now, and again, you've heard this before, is that we have this radial scaling law. So that is, we can sort of draw these lines going outward. And if we scale everything by lambda naught, we get this additional 1 over lambda naught. Then we get this next level and the next level and the next level. And that's exactly what sort of I did down here. I did the reverse part. So usually what we argue is that if we have one of these three-body lines, then we know all the other ones. All we have to do is we have to apply this radial scaling law. Now, what I did in going from the top plot to the bottom plot is I took one of the curves, that is, I took this curve here and I sort of did the reverse scaling. So these are calculated for finite range interactions. It's again very similar to what Alejandro Kievsky talked about, using two-body Gaussians with a three-body repulsion. And so I took this curve here and I scaled it or undid the scaling. And by doing that, I collapsed one set of numerical curves onto the other set. And by looking at these curves and seeing that the lines and the symbols are really agreeing with each other, I'm sort of showing that the two energy levels that we calculated for a finite range interaction really obey Efimov's scaling law, despite the fact that we do have a tiny bit of a range in our system, and we are not working exactly at the zero range limit. So is this figure clear? Is it sort of clear what I'm trying to illustrate with this? So about the cutoff, yeah, that's a really good question, right? So in our theory discussions, what we really like to think about is we really like to think about zero range interactions. And why do we like to think about zero range interactions? Simply because the math gets pretty simple. It's sort of, we have weird objects, we got these delta functions, and sometimes we need to include derivatives and so on. But still, once you sort of get used to it, these interactions are quite nice. Now, physically, okay, so let's think about what does this mean if we say zero range interactions? What it means in some sense is that we can take our interaction, say, between two neutral atoms and their scattering, and we say that all of that interaction happens exactly when the two atoms are on top of each other, right? Remember, in our case, these would be neutral atoms. In reality, what we do know is that if we bring the atoms really close together, right, then we also have our two nuclei overlapping. And so essentially what this means is that we're sort of looking at length scales where we are going beyond atomic physics. So we do have, we are now looking at really, really small length scales, but this is where we actually have nuclei. And so really, really small length scale means we're looking at very, very high energies. And this means that our theory, which is designed as a low energy theory, can't capture that physics anymore. So in reality, there's always a cutoff, and sort of in a way, this is just telling us that, nature in a way is reminding us that we are idealizing and we should be looking more carefully, and there's something inside the atoms. Similarly, if you think about the deuteron, when you might say, okay, what happens when you put the neutron and the proton on top of each other? Well, we do know that inside the neutron and the proton are quarks. And so there's a lot more physics going on. And so we really need to start thinking about the smaller length scales, but we've we've removed them from our problem. So in a way, these cutoffs that we see sort of in our theory that something is needed, that is really a reflection of the physics. Does that make sense, Soroush? Great. Okay, so the key thing that I want to point out here and sort of really drive home now is that with this radial scaling law, right, essentially what we're doing is, what we're having here is we have this radial scaling law. And in a way, we're sort of taking this scattering length, so 1 over the scattering length, and we are taking this axis here, and we're sort of in the radial direction moving right from this point here, say, to this point here, or from, if I draw another ray here, this point here, and this point here. And so to sort of take this curve and this curve and make them collapse, what we need to do is we need to, in a way, scale this axis and this axis, or said differently, we sort of do something to our radius here, and we keep the angle the same, this psi angle, which I've measured from this direction here. So I will refer to this as sort of a 2-parameter scaling, because I need to scale this and I need to scale this. And what we will see later on as I move forward and discuss the Spinorbit coupling system, that we don't just have 2 axes in our problem, so right, x-axis and y-axis, but we actually have 5 axes in our parameter space. And what we will need to do is we will need to be scaling things in 5 or along 5 different axes. Okay. So just sort of a heads up in terms of what we're looking at and what's to come. So the other thing that I want to point out, and that will be useful as we discuss the Spinorbit coupling case a little bit more, I do want to remind you of how these cold atom measurements are being done. So this is the beautiful work by Rudy Grimm's group. What they've done here is they've looked at cesium, and they've really measured the atom losses from a trap at 2 different scattering lengths near this 3-atom threshold, where the scattering length is about -1000 Bohr, and this scattering length, so that would be this threshold here, closer to unitarity, where the scattering length is about -20,000 atomic units. And then they can look at where do you lose the most atoms from the trap, and the losses from the trap should be enhanced when sort of the trimers are in resonance with the 3-atom threshold. And they can measure this nicely and precisely, taking into account sort of different temperatures, set A and set B done at different temperatures. And what they find is that the enhanced losses are really occurring at a ratio that's very close to 22.7. So this is sort of a confirmation of this discrete scale invariance or scaling symmetry in these cold atom systems. And when I discuss the spin-orbit coupling, as I mentioned, there are no experiments yet. And I'm going to use cesium as sort of a toy model just to show you or to sort of illustrate what an experimentalist might potentially be looking for if they can realize the spin-orbit coupling in a system and reach sufficiently low temperatures. So reaching the low temperatures is really the challenging part. Okay, so that was the review sort of on 3 identical bosons. Now I want to actually get into more detail of the spin-orbit coupled situation. So as I mentioned already, it's the single particle dispersion that is being modified. We're going to work as before in the regime where the S-wave scattering length is larger than the effective range, actually much larger than the effective range. And so what we want to ask is what happens to the discrete scaling symmetry? Well, of course, it's a little bit hard to answer because I haven't told you exactly how we're going to modify the single particle dispersion, but I will. What was found is in the case of 3D spin-orbit coupling, in these 2 papers, that actually the 2-parameter radial scaling law will no longer hold. However, there exists a generalized multi-parameter radial scaling law, and the discrete scaling symmetry survives. And this generalized radial scaling law does involve 5 parameters. So this was discussed for 3D spin-orbit coupling and fermions. So these are sort of 2-component fermions in these works. And we looked at this for 3 identical bosons in the presence of 1D spin-orbit coupling. So what I want to emphasize here is that even though the spin-orbit coupling is 1D, the system is still living in 3D. It just means that the single particle dispersion is modified along one momentum direction as opposed to all 3 momentum directions. And so the conjecture from both the fermionic and the bosonic work is that the discrete scaling symmetry should survive for any type of spin-orbit coupling, and there should exist this generalized multi-parameter radial scaling law for any type of spin-orbit coupling. So that's sort of the conclusion. That's the take-home message. So let's take a look ahead and sort of see what does this spin-orbit coupling do? So let me just fairly abstractly introduce this and say, okay, this portion here, all this is the portion of the Hamiltonian that you've seen previously. So all of this here is exactly identical to the ThreeBoson Hamiltonian that you've seen before. There are 2 new pieces. One new piece is this one, and that's just an identity matrix of size 8. And what this does is it basically accounts for the fact that we're going to have 2 spin degrees of freedom per atom. We have a 3-body system. So we have 2 degrees of freedom for the first in the spin for the first particle, 2 in the second, and 2 in the third. So we have 2 times 2 times 2, which is equal to 8 different spin channels. So that's relatively straightforward. And then schematically, and I'll discuss these terms a little bit more as we go along, schematically, we will have 3 additional terms. These are the terms that sort of account for the modification of the single particle dispersion, and that then translates into the 3-body system. And there's sort of 3 parameters. There's a wave number here, KSO. There's an energy omega, and there's another energy delta tilde. And it's exactly these three parameters, so this KSO, the omega, and the delta tilde, that get added to our sort of parameters that we have in our problem. So if we now look at the continuous scaling symmetry, this is what we had before. This is what we had before. And if we add these Spinorbit coupling terms, there are these three additional pieces that we have to add to express what we mean by scaling or continuous scaling symmetry. And that's actually very easy to show that this continuous scaling symmetry survives. The bigger question is what happens to the discrete scaling symmetry? And again, I've highlighted the new pieces, so they're exactly identical to what I've shown here. So these are the new pieces that we have, and what we need to check to see if we still have discrete scaling symmetry is if we do all these scalings here, all of these, sorry, using this omega lambda 0 is 22.7, but we do not scale kappa star, leave that unchanged, do we get the same energy levels? So that's sort of the generalized radial scaling law. If this scaling symmetry, this discrete scaling symmetry survives, then we should have a generalized scaling law, radial scaling law, where we have 5 parameter axes. That would be AS, KSO, omega, delta tilde, and energy. Now, you can already see this is going to be a bit complicated because nobody can actually draw a 5-dimensional coordinate axis and then plot a 6th quantity. So we're going to have to take certain cuts to illustrate that we will have that this radial scaling symmetry, that this radial scaling law survives. Okay, so it's sort of where we are headed. And the next step is really to understand this spin-orbit coupling and to sort of see how does the Hamiltonian actually look like when we have spin-orbit coupling in the system. Are there any questions so far? So it's sort of clear what we're trying to do.
It seems that there is nothing. Indeed, I just have a small comment. Sigma dot P resembles to me the Dirac, dispersion relation for a relativistic particle.
Oh yeah, no, this is a really, really good comment. So if you look at the sort of condensed matter literature and you go through where these spin-orbit coupling terms come from in condensed matter, it really has to do with the fact that the electrons are starting to move at speeds that are close to relativistic. So the key difference that we're going to see here is that we won't just have say P Z sigma Z term, but we're also going to have basically a P squared term. So in some sense, you can think about this as sort of the normal P squared dispersion, but then added to it some sort of Dirac-like dispersion term. That's exactly correct. Thanks for pointing that out, Tobias. Any other questions or comments?
I don't see anything. Yeah.
Okay, so then let's sort of look at this again. Normally, this is our single particle dispersion X, Y, Z. So I've just drawn this again, it's kinetic energy. I call it dispersion, but don't worry too much about the names. So now schematically, let's say we have two different spin states, and each of the spin states can have kinetic energy. So we just have two curves on top of each other. And now let's just assume that the two different spin states have different momenta. So I'm going to shift them. So this is my spin up state. That's my spin down state. And now so far it's pretty boring, because at least based on what I've sketched, we don't actually see any interaction or any sort of talking to each other between these states. And what's going to happen in the spin-orbit coupling case that we're going to look at is there's actually a talking between the different spin states here, and that talking at this point is opening up a gap. Okay, so let's look at this just a little bit more in terms of equations. It's really sort of the same thing that I drew before. So what we have is we have the spin degree of freedom. So we have this term here, we have the two dispersions, and now we have this omega term, and that's leading to the coupling here. And then similarly, you can additionally introduce a detuning, and what that detuning does is it just shifts the two dispersion curves relative to each other. And then, of course, you can still open up the gap here and have the two different dispersion curves or spin channels talk to each other. And that's really all it is. So that's sort of, these are a couple of sketches for the single particle Dirac-like dispersion relations that you can realize in cold atom systems. So let me just take the red one here and sort of highlight where this is coming from, so you can sort of see how this relates to what I did earlier. There's sort of one dispersion curve here. There's the second dispersion curve here. So these are my two parabolas that are offset. And then if I clean this up a little bit again, you see that this is exactly the point here where we have the opening of the gap. And all I've done here is I've illustrated that for different coupling strengths, different Raman coupling strengths, omega. So the red curve is relatively weak, then the blue curve, the gap gets bigger, and the black curve, the gap gets even bigger. In the left plot, I've done this for zero detuning, so delta is equal to 0. And in the right curve, there's a detuning, so there's sort of an offset and an imbalance between the left and the right curve. So now you might say, why is this interesting? Just to give you one example, if we look at the expectation value of this del H, so this is just our single particle Hamiltonian, we see this group velocity here. And very clearly, if you look at the group velocity along the Z component, you see it increase, decrease, and increase. So there's a rather unique velocity, group velocity associated with a dispersion curve that has a minimum at finite momentum, goes to a maximum at momentum 0, and then goes and has a second minimum. Okay, so this is nice. You might ask, how can you actually realize this experimentally? The way you do this is, and that's been pioneered by Ian Spielman at NIST, following a number of theory proposals. But essentially, what you can do is you can take two different hyperfine states in, say, rubidium, and you can couple these two different hyperfine states with two lasers. So we have a two-photon process that couples this hyperfine state with this hyperfine state. And we're going through a manifold of excited states here. which at the end get eliminated. And this is our high energy Hilbert space, and we don't have to worry about this. So effectively, by having these lasers here, so we have sort of a photon being absorbed and being emitted, we couple the spin degree of freedom here with the spin degree of freedom here. So you can sort of think about this as you have these photons or these lasers coming in, and there's photon emission and absorption going on. The atom gets a kick. And by connecting sort of these two different hyperfine states, that also involves the kick that the atom gets, and that involves the momentum. So this is sort of how, at least intuitively, you can see how the spin momentum coupling comes about. Just to give you a little bit of a feeling for things, the inverse of the wave number is of the order of 2000 angstroms. So this is in the rubidium experiment. So this is actually quite a bit larger than the effective range of the atom-atom system. And then the spinorbit coupling strengths is typically the energy scales are sort of the order of a few kilohertz. So that's actually quite a bit of energy. All right. So we have the single particle dispersion, and again, I just sketched this here. And before I come to the bosonic system, two boson, three boson system, I just want to give you one more example of why these modified dispersion curves are actually interesting. If you take the eigenvalue here, the lower lying one, E minus, and you just expand it for large omega around the minimum value, you see something, you see an energy that very much looks like as if we had a charged particle in a uniform vector potential with the vector potential given by this term here. So the excitement, quite generally speaking, is that even though we have neutral atoms, with these techniques, we can actually design, we can engineer dispersion relationships and behaviors that emulate the Hamiltonian, the expressions that we are used to seeing for charged particles. So it's a really nice tool. And so the hope, that sort of a big motivation was to then look at, for example, a fractional quantum Hall effect with neutral atoms. So this is sort of one of the broader motivations for manipulating these single particle dispersions, going beyond few body physics. Okay, so the next thing that I want to do is I want to discuss a little bit the solutions to the two boson and the three boson problem. And so to do this, I want to discuss one numerical technique, and then I sort of show you results and sort of illustrate that discrete scaling symmetry really survives. So let me just ask, do people want to take a 5-minute break?
Doerte, I think it's good to stop for 5 minutes, no? It's
Okay.
a good point to rest a little bit. So is 5 after the time is fine?
Yeah, no, that sounds
Okay.
good. So we'll meet
Okay.
again 15 after.
Yes. 15.
Okay,
Okay.
that sounds great. Thanks.
Okay, Doerte, I think we can continue.
That sounds great. Thank you. Yeah, so we're sort of ready now to look at the two-body and three-body problems. We have a first feeling for, how does the single particle dispersion looks like? It looks very different. And of course, what we expect is that if the momentum without the interactions, just the kinetic energy is quite a bit different from the normal p²/2m behavior, then what we expect is that the binding will also be probably quite a bit different. And I'll discuss this. So what I've written down here is I've written down the two-body Hamiltonian, the two-boson Hamiltonian. Actually, at the moment, this would also apply to fermions in the presence of spin-orbit coupling. And what I should, sort of another really neat thing about these spin-orbit coupled systems is that we are now actually looking at bosons. So these are composite bosons, rubidium-87 atoms, they're bosons. We're looking at those having spin. So we're looking at bosons with as effective spin 1/2 systems, and that is because they have the hyperfine structure. All right, so again, the details are, and are not that important. They're fairly intricate, but I just want to highlight a few things here. This is sort of our normal kinetic energy. So first, we have our total Hamiltonian for two particles, and we can divide this into relative and center of mass piece. And this is very similar to what we normally do. However, there is a big difference, and that big difference is that the relative Hamiltonian does in fact parametrically depend on the z component of the total momentum. And the z component comes into play because we have the spin-orbit coupling directed along the z direction. So if you look at this last term here, this is where the center of mass Hamiltonian the center of mass momentum comes in. And what this means is that we really have to solve the relative Hamiltonian for each center of mass Hamiltonian. So there's actually a broken, the Galilean invariance is broken. So it's quite an interesting system. And then the other thing that we have is this is coming from the detuning. So the sort of physical detuning combines with the center of mass momentum, and we call this sort of an artificial or combined detuning delta tilde. And then what we have is we have the coupling between the spin and the momentum, both coupling of the relative momentum to the first spin and relative momentum to the second spin. And then we have the Raman coupling. So this is the term that in the single particle Hamiltonian gives rise to the opening of the gap that I discussed. And then we have the two-body interaction. And we now have, right, we have each atom has spin up and spin down. So if we have two atoms, so we have two spin states here and two spin states here, then we have interactions between each of the spin states. Okay, so that's sort of the structure of our Hamiltonian, and this is sort of the Schrödinger equation that we need to solve. So let's sort of think a little bit about what are the demands on whatever numerical technique that we want to use. That we have. So what we need is we need to be able to describe multiple channels. We need to be able to describe small and large length scales because we're going to use the two-body potential with a finite range, but we also know that our S-wave scattering lengths should be large. What we want is, we want to describe eigenenergies and eigenstates that vary by orders of magnitude. But remember, at unitarity, if we look at two neighboring energy levels, their spacing is 22.7 squared. So that's of the order of 500. So if we want to look at three different energy levels, then we have sort of very different energy scales that we need to resolve, right? We would have a factor of 500 here and a factor of 500 here. So this really is quite demanding from the numerical point of view. And then what we want is, we would really like a technique that's applicable to both 2 and 3 particle systems. And, just as Alejandro Kierski said, everybody, there are multiple different techniques out there. We do want to describe ground state and excited states, but still there's several techniques out there. And, different groups have different preferences, and to a large degree, it just sort of boils down to, what are we familiar with? And in my case, I've utilized the stochastic variational approach quite a bit. And I think I can go through this part relatively quickly, because there was already a nice discussion of that yesterday by Roy Yaron on the in the contributed talk session. So let me just sort of go through what is the basic idea of this approach, and to kind of set the stage. Let's start fairly general. Let's say we have an orthonormal basis set, denoted here by this phi. And I'm sort of schematically indicating the orthogonality by vectors that are at a right angle here. Of course, it's a high dimensional space. I can only draw a few of these. And of course, from quantum mechanics that if I have a given eigenstate of a system, I can expand this in terms of this complete set of states. And we have these expansion coefficients. Of course, in reality, we can't go to infinity here. So we need to cut this off when we have a finite number of basis states. And, sort of generally speaking, what you would expect is that, the bigger this is, the more accurate your description is. And that's true. However, we can also, and we will have a choice of what we are actually using for our basis states. Sometimes plane wave states are pretty good basis functions, but sometimes harmonic oscillator states are better. And so depending on what you use, you might get away with relatively few basis states, or you might need quite a lot of these states. And then if we take these expansion coefficients, we collect them in a matrix. So this is my symbol for a matrix here. Then we have an eigenvalue equation of this form. We can diagonalize this. And what we find is that the eigenvalues of this finite size problem, because we've now cut things off here at a finite number of basis states right here. So the eigenvalues of this problem here of this matrix equation provide variational upper bounds to the exact energies E0 and E1 and E2 and so on. And this is really the variational principle that underlies many techniques, and you already heard about that this morning. So what I want to do next is I want to use a set of basis functions that are not orthogonal. So schematically, drawing this would mean that my basis states don't actually have a 90-degree angle they're not orthogonal, but they have a linear dependence. So if we do this, what changes? In particular, how does this eigenequation change? Any suggestions? That's right. You need to consider the overlap. That's very important. So if we put this in and we write this out, this overlap is going to show up here. So this is the new piece that we get because we don't have orthogonality. And this matrix O is, or the matrix elements are defined here. So it's really the overlap of our two different basis states. And essentially you can think about it as, right, if your states are actually not orthogonal, they have a linear dependence, then you sort of need to take out how much they are actually dependent on each other. So this is just meaning that you get a generalized eigenvalue problem. However, the important point is that in fact, we still fulfill the variational principle. So whatever eigenvalues we calculate, they still provide upper variational bounds. And so this is really nice. So basically, what does this mean? This means that we have the freedom to choose whatever we want. So this is what I wrote down here. Right, these basis functions, they can be anything. They might be, we can construct them sort of to our liking. And okay, what do we like? We like to have basis states such that all the matrix elements can be calculated very quickly and compactly. Ideally, like to have analytical expressions so we don't have to calculate matrix elements numerically. And then the other thing that's very important for our problem is what we would like to do is we would like to choose our basis states in such a way that they really cover the different length scales in a very nice way. When I told you that the scaling factor, you know this by now, forward and backward, the scaling factor is 22.7, right? So I want to be able to pick one sort of basis state that describes physics on this length scale. And then I want to try to pick another basis state that describes the physics at scales that are 22.7 times bigger. And you can already see, even by hand, I can't actually show the dramatic change of length scales. And then the other thing we do, and again, this is very similar to what Alejandro Kievsky already talked about in quite a bit of detail. We want to take advantage of the fact that we can construct a low energy Hamiltonian. So we're going to use Gaussian interactions at the two-body level. We stabilize the system by a purely repulsive three-body system. And then, of course, we have the spin-orbit coupling terms, and we have the kinetic energy. So that's sort of the general setup. This stochastic variational approach was, at least to the best of my knowledge, first used in the ultra-cold atom context in 2005 by Sorensen, Fedorov, and Jensen. And then it's really been used by a number of people. If you do want to get a nice overview, this textbook by Suzuki and Varga is really excellent. And it has anything that you ever wanted to know. It's really beautiful. So we want to use these basis functions. We are pretty much going to use Gaussians to start with that have different ranges. And we can sort of pick functions, Gaussians, that have a size of the range of our interaction. And then we can also pick much, much bigger Gaussians that really describe the size of our bound states. And we do all of this using Jacobi coordinates. Okay, so if we sort of carry this out, there's one other thing that's quite important. So there are these non-linear parameters here. So, you know, I've emphasized we want to use different sizes of Gaussian, and the size of these basis functions is really given by these parameters D. And so these are our nonlinear variational parameters. And then essentially what we do is in a somewhat smart way and sort of motivated by physical arguments is we try to pick the sort of length scales or the sizes of our basis functions in a smart way. Sometimes smart means that, you know, physics tells us what to use, and other times it just means let's do try and error. So before we decide this is a good basis function, let's just try and look at many possibilities and sort of pick the best one. And that's exactly what I outlined here. So usually what we do is we start with our first basis function, and then we want to add a second one. And what we do is we don't just pick one, we actually look at, you know, say 100 or 1,000 or 10,000 different possibilities. And then we pick the one that lowers the energy the most. And so the idea is we try a lot of functions, but we only pick the best ones. And this allows us to maintain a pretty small basis set. And we sort of run through this and we repeat this. And another key advantage is that we can sort of target the state. So we can either optimize the ground state of our system, or we can optimize an excited state of our system, or we can actually optimize multiple states simultaneously. So there's a fair bit of flexibility within this approach. And this just shows you how this sort of works for 5 bosons in a trap. So there's no Spinorbit coupling at this point. We add the first few basis functions and you see how the energy goes down. We're at about 6.08. This is just atoms in a trap. And then, you know, this is where we are. Now I'm switching to 1 over the number of basis functions. And then essentially all the work is being done here, where we add 1 basis function at a time to then get pretty nice convergence to 5 digits or so. This is just one example. And here we really chose about 1,000 or a few thousand each time that we added the basis function and then kept the best one. Give you just a different example, you know, we already discussed, we're very interested in sort of emulating zero range interactions. So here we looked at a system with 3 up fermions, 3 down fermions. And what we're doing is we're changing the range of the interaction, and we're trying to see how do things look like in the zero range limit. So we perform calculations at different ranges and then extrapolate. This is for the energy, and this is for the pair distribution function. And then this here is the short distance region, where you see that the system is sort of converging toward the zero range limit. So again, this just sort of shows you this approach works, and we can go to, I think for the trapped fermionic system, we've pushed this up to about 10 particles, but the calculations do get pretty big. Okay, so just as was mentioned earlier, also by Alejandro Kievsky, we are sort of running into the same problem. We need to symmetrize our basis set. If we have 5 identical particles, it means 120 permutations, and that really, that can make the simulations, the calculations quite extensive. And then, as I mentioned, we can sort of use physical insight if we know that the system consists of a dimer and an atom, we can sort of put that in and choose basis functions that have that property. Okay, so far I haven't actually accounted for the spin. So I had this Gaussian piece in our basis functions, and now what we do is we add this spin piece to it. So depending on what spin channel we are in, so this is characterizing or determining which spin channel we are in. We have this piece here, and this piece, among other things, allows us to treat systems that don't have a good orbital angular momentum. Okay, so that's sort of all I wanted to say about the method. And I thought I'd just show you a couple of results for the two bosons with spin-orbit coupling, and then 3 bosons with spin-orbit coupling. Okay, does the code run on a classical computer? Yes. Are there schemes to generalize this to a quantum computer? Not that I know of. I don't see how to transfer this particular scheme to a quantum computer. Okay, there are any other questions on the algorithm? You know, again, that was just sort of an idea, you know, give you an overview, give you a little bit of a feeling for what techniques are out there. So let me move on and show you just a couple of results for the 2-particle and then the 3-particle system. Again, this is sort of the system that we want to simulate and describe. And let me jump to basically what we're seeing in the 2-particle sector. So when we have 2 particles, what we looked at is we looked at both 2 identical bosons, and we looked at 2 identical fermions. For our purposes here, we're not so interested in the 2 identical fermion case, so I suggest you just ignore this part here. And so what I do want to sort of focus on here is the following. So I want to look at the case where we have an infinite scattering length, and I've plotted the scattering lengths here in some sort of slightly, you know, say weird units. I use the spin-orbit wave number, spin-orbit coupling wave number as my scale. But essentially, let me just draw a straight line up here. And let me just point out that if we didn't have spin-orbit coupling, then what we know is that on this side here, we would have a 2-body bound state. So we would have binding. And on this side here, we would have no binding. Right? Positive S-wave scattering lengths, we have a weakly bound 2-body state. Negative scattering lengths, we don't have a weakly bound 2-body state. And now what you see is that the, let me just switch the colors here. What you see is that the binding is extended way into the negative scattering length side here. So what do we have? I fixed this sort of spin-orbit coupling. I've used the KSO as my energy and length scale. And on this axis here, I'm changing the generalized detuning. So don't worry about it too much. Just sort of think about this as I said, we have 3 new scales when we have spin-orbit coupling. I mentioned this KSO, the omega, and that delta tilde. And what I've done here is I've used this to define my lengths and my energy. I have fixed this at this value here, and then I'm changing my generalized detuning on this axis. And what you see is that due to the modification of the single particle dispersion, we actually get more binding. So the two-body system is bound more than it would be in the absence of spin-orbit coupling. So that's sort of the key message that I want to sort of bring or point out. And I can also give you a bit of a physical picture of why this happens. So again, the sort of region where we have now my infinite scattering lengths is here. So all this region here is enhanced binding. And what I'm doing here is I'm looking at, just this negative scattering lengths here. And I'm looking at 3 different generalized detunings. And what I'm plotting in this plot here is the momentum space distribution. And then here I'm plotting the real space distribution. And the sort of key point is that when we have this maximally enhanced binding, because the binding really goes out way to the left here, that is the case where our dispersion has multiple minima. So our momentum distribution is really spread out. And because we have a broader momentum distribution, we have a narrower wave function in real space. And a narrower wave function in real space simply means that we have a deeper or more deeply bound state. So very intuitively, you can think about the fact that if you modify your single particle dispersion, what you do is you give the system either more or fewer opportunities to sort of play around in that momentum space of or the sort of range differently in terms of what momentum the system takes. And if we have sort of a broader dispersion curve, and if we have sort of these 2 minima here, or even 3 minima at the bottom of our relative dispersion, then this actually leads to enhanced binding. Okay, so this is in the two-body sector. So what this means is that we have to be careful in terms of, right, where do we have a two-body bound state and where do we not have a two-body bound state? And of course, if we look at the breakup of our three-body system, we need to take that into account, right? Where do we have a two-body bound state that our three-body system can break up into? And of course, we do take that into account in our calculations. So now we're ready to look at the ThreeBoson system. So again, what we want to see is whether or not we have this discrete scaling symmetry. So this is the question that we want to answer. And so essentially what we need to do is we need to perform calculations for different scattering lengths, different KSO, different omega, different delta tilde. We need to look at what is the energy of our system. And then we need to see if we apply the scaling, if we, scale the scattering lengths by lambda naught, KSO by lambda naught to the -1, and so on. We need to see if the energy levels collapse. So let's take a look. As I said, in general, what we want to do is we really want to sort of have a 5-dimensional space. So at the danger of sort of embarrassing myself, we want to have 1, 2, 3, 4, 5 axes. And then what we want to do is we want to sort of look at a given energy curve within the space, and then we want to scale things and see if we collapse to the next curve. And the scaling law is again a radial scaling law. So if I have my 5 axes, say I label my axes with y1, y2, y3, y4, y5, then the lengths associated with this would be the absolute value of my vector y, which is the square root of y1 squared plus y2 squared, so on, plus y5 squared. So we're really sort of looking at a generalized radial scaling law. Obviously, I cannot sort of do this. I can't do these plots. So what we did is we looked at examples. So here our generalized detuning is 0. And my axes are the scattering lengths, or the 1 over the scattering lengths, and energy. So this is very similar to what we had before. This is our three-body energy. This is our dimer threshold. So it looks a little bit different from the case without spin-orbit coupling. And then what we do is we basically perform one calculation for a fixed KSO and for a fixed omega. And then what we do is we scale the KSO, we scale the omega according to what we would expect. That is, we stick that lambda naught factor in there as we are supposed to. And then we perform another calculation and we find these energy levels. Again, we plot that as a function of 1 over the scattering lengths and the energy. And then we apply the scaling. And what you can actually see is that this energy level and that energy level totally collapse. And that collapse is confirmation of the discrete scaling symmetry. So we didn't map out our full 5-dimensional hypersurfaces because that's just incredibly difficult. But we looked at particular cuts through this 5-dimensional hypersurface. But it's not just a cut in a particular plane, it's a cut that sort of takes that radial scaling law into account. Okay, and then we've checked this for many other cases. And again, in all cases, we see really, really nice collapse. And so this is confirmation that, yes, indeed, the discrete scaling symmetry survives. And yes, there exists a generalized radial scaling law if we look at the ThreeBoson system with spin-orbit coupling, and in our case, one-dimensional spin-orbit coupling. So let me skip the sort of proposal that we have for observing this experimentally and sort of just summarize and say that I did discuss one few-body technique in a little bit more detail today, the stochastic variational approach with explicitly correlated Gaussians. And then I applied that to bosons in the presence of spin-orbit coupling. And I discussed, I motivated where does the 1D spin-orbit coupling come from. And then I showed you a couple of consequences of this in the two-body sector. And hopefully I was able to convince you that this radial scaling law also holds in for 3 identical bosons with spin-orbit coupling, and more generally, any 3-body system with spin-orbit coupling, where the 3-body system without spin-orbit coupling already supports the Efimov effect. And so with this, I just leave you with 2 references. and really thank Chingze Guan, who's done a lot of the work both on the ECG approach and also in working out this generalized radial scaling law. And then also point out 2 former students in my group who've worked quite a bit on the explicitly correlated Gaussian approach. Thank you.
So thank you, Doc. Thank you very much for this nice lecture. Some questions to Doerte? No questions?
Does this mean I lost everybody along the way?
No, not yet. People are still around. I mean,
No, I mean, okay,
yeah.
can I talk a little bit more about connections with experimental attempts to verify this? Yeah, so I really should point out that at this point, I'm not aware of any experimental groups that have attempted to look at this. What we were thinking about is the following. So let me sort of point out and discuss a little bit the way we were thinking about this. This is again the 1 over scattering lengths plot here. If we didn't have spin-orbit coupling, this is the scattering lengths at which the Threebody losses would be enhanced. Now, if the 1D spin-orbit coupling is turned on, our prediction and our calculations show that as a function of this generalized detuning, this is where we also have Threebody bound states existing. And as you can see, this extends from a scattering length, in sort of this, for this example, a scattering length from about -8,000 Bohr to about 20,000 Bohr. This is where in the cesium experiment without spin-orbit coupling, they had seen enhanced losses. And so sort of our first thought is that it would be nice to see that if the spin-orbit coupling is turned on, that one would actually see enhanced losses, not only at this point here, but into the region where the scattering length is a bit smaller. So they're really seeing and verifying that 5-parameter scaling law is going to be extremely, extremely, extremely challenging. And this, as I mentioned, this generalized detuning sort of has the center of mass momentum in it. So maybe if we are looking at a thermal gas, some of these trimers are already occupied. So I think Janis and Eloisa, both of you asked the question. Does that sort of give you a little bit of a feeling of what we're thinking of? So these would be extremely, extremely challenging experiments. So, we're not gonna tell the experimentalists, hey, here's a 5-dimensional hypersurface, map it out. Then they're gonna, not, it's just incredibly challenging. So we've been thinking about sort of other observables that would at least give a hint at what should be there.
Thank you.
Yeah, thank you for the question.
Other questions to Doerte? Oh, I don't see any more curiosity at this point. Maybe for tomorrow we have new challenges.
It's been a long day for everybody,
Yeah,
right? A lot of lectures and talks. So yeah, thanks for coming. Thanks for sticking around till the end. And see everybody tomorrow.
Tomorrow. Thank you, Doerte. Thank you very much. See
Thank
you.
you. Bye-bye.
Goodbye. Goodbye.